Alrighty, I fear this may be the longest notes video yet, but I'm going to try to keep it moving, talk quickly-ish, so we don't be here for an hour. So, looking at the top here, we are moving into the next section, 1.4, which is a study of the topic of continuity, right, as you can see at the top. And then also, we're going to get one of our first big theorems here, which we're going to refer to as IVT, the intermediate value theorem. So this is the first out of 4 theorems that we need to know the if and then portions of by heart so that we can cite it in our work when we do free responses and things like that. So I'll reference that later. But for now, let's just focus here where it says what continuity is. Our intuitive understanding of continuity is that if you can draw a function without picking up your pencil, that function is continuous, right? But that's not the mathematical definition, okay? We're going to get down to that definition down here. But before we do that, I want to talk about some things that kind of break up continuity. Right? So when you think about graphs and you think about things that get in the way of your ability to draw a function without picking up your pencil, what kinds of things cause that to happen? Okay. All right, so hopefully you answered that. So the things, that we could have thought of in our brain. First one is a hole, but that's probably not the first one that came to mind. I would imagine that most of you, if you thought enough about it, thought of a vertical asymptote, right? And that asymptote gets in the way of us drawing without picking up our pencil because we have to draw the asymptote, right? And then we have to pick up our pencil to get over the asymptote on the other side. The last thing is kind of a new one. This year we're going to call it a jump discontinuity, okay? So when you think about the absolute value of x over x function that we've kind of studied again and again this year, right? It's that function that looks like this, right? And it's got this going on here, and it's got this going on here. I know it has these holes, but it's the jump feature from one branch of the graph to the other that qualifies it as a jump, okay? So that's technically a jump continuity. All right, and then let's talk about what we would classify these as, right? So if I'm classifying a hole, we call that a removable type of discontinuity, which means there's only one value in the whole graph that actually causes us to pick up our pencil, right? The other two in this list are what we call non-removable discontinuities. Someone will have to check my spelling on non-removable. I don't know, is there an E in there or maybe not an E? I don't know, you'll have to Google that. But I should know that, but it's just not clicking right now. So anyhow, we've got non-removable discontinuities. Just means it's a little bit more invasive, right, of a discontinuity. So now that we know the things that kind of hinder continuity, let's talk about the actual definition of continuity. Because as you see down here down the page, we are actually going to end up looking at these functions here and talking about what the definition breaks up. So in order for a function to be continuous at a point C, so we're talking about at a specific x value, 3 conditions need to be met. The first one is that the function needs to be defined at that point. Okay, so that means at the x value C, you have to be able to plot a y value. That's all that means. The next thing is that the limit as you approach C has to exist. Okay, so the limit has to exist there. And then lastly, this is kind of where the definition gets wrapped up with a nice little bow, is that the function's definition in part 1 has to equal the limit that exists in part 2. So down here, we would say that the function's value actually equals that limit at that point, okay? So you can't have any one of these 3 things. I mean, truthfully, we just need the third one to be true, and then we're good. Because that indicates that both of the other 2 are true. But let's go down here and let's kind of look at graph A, and let's decide which of these is met. So I'm just going to use like 1, 2, and 3 to talk about what is met and what is not. So if we look at the value of C equals 1 in graph A, right, where that asymptote is, let's ask ourselves, is part 1 true? Is the function defined? And obviously, since there's no y value along the asymptote, we could say that number 1 is not true. And then, is the limit existing there? No, it doesn't, because of that asymptote. And then, of course, 3 can't be true because neither of the other two, okay? So here we have none of the conditions being met. Let's go over to B, okay? Let's look at c equals 1 again, on this line here, and decide, is the function defined? Right? Yes, the function's defined because we have this point right here, right? We have -1 for the y value. So we would say part 1 of this is true. Does the limit exist here at 1, right? And we would probably say no because our function's going to different values there, right? So condition 2 is not met, and therefore since condition 3 is not met, or since 2 is not met, 3 can't be met. So the only one that's true here is part 1 of the definition. Okay, let's look here at graph C. Graph C, the function is defined. We've got this point at 1, 2, so 1 is true. The limit does exist, right? Because as I approach from the left and the right, both of my limiting values come to the number 4. So the limit does exist. And then do we think part 3 is true? Does the limit equal the function value? And of course that's not true, right? Because that little hole that point at 1, 2 is not filled in where that hole is. So that's why condition 3 is so darn important. If that point had been filled in where the hole is, oh my gosh, it would be continuous. Okay, and then lastly, let's focus here at this point, 1, I don't know what this function is, so let's say 1, 27. The limit exists, the function is defined, right, because it's a nice smooth function there. The limit exists, right, because from the left and from the right, I come to that same point. And then lastly, the limit actually equals the function value. Ding, 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 we have a winner. So this guy is continuous, again, based on those definitions, okay? Yay. All right, let's advance then through continuity, and let's look at this fancy problem they give us when we have to, once we know a function is continuous. So this question is asking us to find this value of a in here, in these two pieces of this piecewise function, so that f of x is continuous, okay? So that means the function's value equals the limit at that point. So I want you to think in your brains, right, about that part 3 having to exist, and that's kind of what steers the information we're going to write down. So what we need is we need this side of the function to equal this side, basically, right? And we specifically need that to happen at x equals 1, because that's where the transition occurs from one piece of the graph to the other. So what I'm going to do is I'm going to put in 1 for the x values here. So a squared, and then let's make it green. Plugging in 1, go back to my purple, 3a, subbing in 1, again for the x value, and then minus 2. And now I have this equation that only has one variable. So I should be able to solve this, right? So I get negative 5a squared equal to 3a minus 2. That's a quadratic, so you've got the option to use the quadratic formula if you love it, and then you also have the option to try to factor this bad boy if you are good at factoring. So in order to factor it, right, I'm going to get everything on one side. Now, this is just truth about Miss Rand. I was never taught to do trial and error here. So some of you, right, you know how to factor this right now where you see negative 5 as the a value, and you start putting in some stuff here and here, and then you think about what goes in here and what goes in here, and I suck at that. So I was never taught that way, so I can't do it. So those of you that can, go ahead and do it. For people like me who can't, I'm gonna show you how to split the middle, right? So I'm just gonna take this work up here. So if you never learned how to split the middle, right, we are going to multiply a times c. So I still write mn. I remember learning this in 7th grade, and we called it the mn method, but mostly we call it splitting the middle now. So m times n, which is really a of negative 5 times c of 2 is negative 10. and plus n, where I add the two numbers together, has to be the middle term b, which is -3. And now I'm going to sort through my list, right? It could be 1 and 10, or it could be 2 and 5. And then I have to pick the signs in the way that they add up to -3. So I'm going to pick this with a -5 there. And now I'm going to split up the middle. I'm going to change this -3a to a -5a and a +2a. That's where the splitting the middle title comes from, right? Set it equal to 0. I'm going to factor out -5a over here. A minus, no, +1. And then I'm going to factor out a 2, GCF of the last two terms, and be left with a +1. And now I know that I've got -5a plus 2 as one factor. I've got a +1 as the other factor. And then I can solve, of course, each of these individually. So thank you, zero product property, set that equal to 0. Subtracting 2 and dividing by -5, I get 2/5. And if over here I set that equal to 0, I get a equals -1. And those, friends, are my two answers. So this particular graph has two answers for a that will make this function continuous. Okay? Cool, cool, cool. All right, now let's go ahead and look at the intermediate value theorem. So as soon as we learn about continuity, the first thing the AP World throws at us is this theorem, right? That involves a function being continuous. So the way this function reads, it says if f is continuous on the closed interval a, b, and that f of a does not equal f of b, that just means the y values at those endpoints are two different numbers, and k is any number in between f of a and f of b. Okay, so that means that k is a y value. Okay, then there is at least one number c in AB, so that means that c is an x value, such that f of c equals k. All right, now you read that, it don't make any sense. I swear, I know, it doesn't. But let's look at what they're really trying to say. So let's pretend this function here, let's pretend this is a, and let's pretend this is b. Okay, so what I'm going to do is I'm kind of think about the little window of this graph. Actually, picking these two is not very helpful to you guys. I'm going to pick new a and b values so that it's easier. So let's pick a, let's pick a to be here, and let's pick b to be about right here. Okay, so now I'm going to look at, so f of a, right, is 0, because that's the y value at that point, and f of b up here is, I don't even know what these numbers are, let's say 2.6, okay, and so that's the y value there. So what I kind of imagine in my head is this scenario, okay, I kind of imagine like almost like a special little window, okay, so I'm going to kind of draw this window for you here with my orange pen. Okay, and in this window then, oh geez, these are where we are for sure that this function passes through all of these x values along here. So here's the c that we were talking about, and then on the y scale, we're super sure that this function passes through all of these y values, okay? So k is any number, right, between f of a at the minimum end of this function and f of b at the top, okay? So that means k is somewhere in there. So somewhere in this box, right, we know that we can find an x value that has a y value. That's all it's saying, okay? What we don't know is that nowhere outside of this box, right, are we sure that functions exist at certain values, okay? So let's assign some numbers here and see what makes sense. So what I'm trying to say here is that going back, right, in this box, if I ask you if this function passes, let's say, you know, if we agreed that this f of b value, if we agreed that that was like 2.7 or whatever I said, then do we know that this function could go through 3 or 4, right? And I would say no, because 3 or maybe this is 3, and this is 4 up here, we are not sure that the function is going to pass through those values because they're outside of this box I created, okay? But let's think of a k value that is inside the box, right? Let's take k equals 1. So right here, right? Are we sure that this function passes through k equals 1? Well, yeah, we are, because 1 is in between 2.7 and 0. So since that k value is in this little box that we created, we're sure that it's paired up with a c value in this window as well. Okay, now the same thing could exist. If I look at this box again and I want to know, does it pass through -3? Well, no, because a and b were the limiting values on the x side of things that this function passes through. So let's say that's -1 and 1/2 or something, okay? So let's look over here. In particular, let's look at this function and ask, does this function pass through the, let's give you the interval here of -2, and let's make our other endpoint +2, okay? And let's ask you, does this function pass through, let's say 4? Okay, so I'm going to think about that window. So from here on the x-axis, and then I'm going to go up. Oh, I just kind of drew that wrong. I'm going to go up to the f of a here, and then f of b over here on the right. I'm going to think about this little box. Okay, now, apparently this function only passes through the points between this y value here on the left and this y value here on the right. And since 4 is outside of this box, no, this function does not pass through it. Okay, now let's think about f of x equals 1. The number 1, right, highlighted here, that is in the box, right? But this function actually doesn't pass through 1, right, because it has a horizontal asymptote. And the reason why it does not pass through 1, we can't guarantee that, is because this function is not, as we said before, the condition. It's not continuous on this closed interval. Since there's that asymptote at 0, we can guarantee nothing about the y values that this function passes through. Okay? Last 2 examples here to kind of hopefully, I think these 2 examples will give you more clarity, because thinking back to our skills as a learner, right, if these graphical interpretations of the intermediate value theorem don't work for you, then let's consider down here this numerical representation, and I bet this clicks. So for this question, it says, it's known to us that this function is continuous on 312. So that's the given information. So what this implies to us, right, is that the intermediate value theorem holds true. There's no holes, asymptotes, breaks, so that means what I see is what I get. Okay, so question A, does f of x equal 0 for some value of x in 3 to 12? Okay, so remember, here's our x values on top row, and then our y values are on the bottom row, right? So if I look in 3 to 12, right, I can only look at the values that are listed here, okay? So I'm seeing here that f of a is -1 and f of b is 2. So that means, on the y-axis, the lowest that it goes is -1, the highest that it goes is 2, okay? And so since 1 is, since 0, the point in question, right, is right in the middle of those 2 numbers, I can say yes, right, yes, f of x equals 0, or I guess I should say, oh no, that's fine, f of x equals 0, because f is continuous. We're going to work on this justifying, and f of f of 3 equals -1, and f of 12 equals 2, and we have to say 0 is between -1 and 2. So we're citing the ifs and the thens of the theorem, to give us that justification. And we'll do a con exercise where you get to practice that more. Okay, let's try this again for the number -7. So same idea. I want to, I've kind of got the same y values here. Now, what I do know from this table, right, is that since this function is continuous everywhere, you're probably thinking like, oh, -1 is the endpoint in 2, but I know, right, let's use those endpoints again, -1 and 2. I know that it goes through these other values like -4, right, further down the y-axis. I'm looking at this point in the table. And then at -5, I'm looking at that point in the table. So since we know this function is continuous, right, we can look outside there, because now each little subinterval is, the intermediate value theorem is true on each little subinterval, okay? However, this particular question, right, asks us about the number -7. So -7 is outside of the window that we're thinking of for our y values, okay? So we would say to this one, no, f of x does not equal -7 because f of 3 equals -1, and f of, oh, let's not say that. Let's say because on any continuous subinterval, in the table, no value goes lower than -5. Okay, so that would be enough. We have continuous subintervals, and what I'm saying here, right, is that when I look at this table, I am noticing, right, I've got this subinterval. Nope. I've got this subinterval. So I know that it passes through all the values between -1 and -4, right? But only between the x values of 3 and 4, okay? I've also got, of course, the next one here. I know that only between 4 and 10 could this function pass between -4 and -5. I don't know anything else other than that. And then I know the last one, right, obviously here, between the values of 10 and 12, I know the function goes from -5 to 2, but I don't know anything outside that, okay? But if we're looking overall at the big interval, right, we know that this function does not pass through -7 at any point, okay? If I had asked you if it passes through, let's say, -3, you would say yes, right? Because -3 is in one of those subintervals. This first subinterval guarantees that this function passes through -3 on the y scale, between the x values of 3 and 4 on the x scale, okay? And we know that because those subintervals are continuous as well, okay? So this theorem is a lot to take in, right, in the first couple weeks of school, but we'll work with it more and it will become more clear.